Welcome to this, the first of our 3-series program dealing with topic 17, an equilibrium. I want to start by looking at a tool that's used to solve equilibrium problems, sometimes referred to as the ICE table. ICE is an acronym. That acronym stands for knowledge of the initial concentrations of the species in your reaction. C is the change in those species. And finally, E refers to the equilibrium amount of those species. Now, a few things about the use of this table to solve problems. The first thing is all information that's presented in the table has to be presented as concentrations. So you don't want to leave things in moles. So if I take a look at this problem, I have a 10-liter container and 5 moles of PCl3. So I have to take this number of moles and divide by the volume in order to place it here in the table. So 5 divided by 10 means that the initial amount of PCl3 is 0.5. In a similar fashion, 4 moles of chlorine divided by 10. And there is no mention that there is any product present, so I'm going to make an assumption here that that is 0. And at equilibrium, though, I'm told that there's 3 moles in the 10-liter container. So 3 divided by 10 gives me this piece of information down here. So that's how I begin to fill out my ICE table. That's the information that's given to me in the problem. The next thing I'm going to focus on is the change column, how much things have changed by. And the use of the change column also means we have to pay some attention to the sign of that change. Is the amount increasing or decreasing? So in this case, I can notice that I started at 0, I've gone up. So positive 0.3 is the change. If these concentration is going up, that's telling me the reaction's proceeding forward, then it can only come at the expense of these two reactants. They must be going down. Now, how much they go down by, that brings us up to the third point in the use of ICE tables. The data that goes into this change column must reflect the coefficients of your species. They must be in the same ratio. So this is 1 to 1 to 1. So all of these changes would be by the exact same amount, 0.30 and 0.30. Once I have knowledge of the change, then I can figure the equilibrium amounts out. 0.5 minus that. So there are my answers. That gives me the equilibrium concentrations right here of the 3 species that are present. Let's look at this graphically. So we start off with PCl5 somewhere up here, and then it drops down to about 0.2 somewhere down here. So there's what's essentially happening to the PCl3. Chlorine starts off a little bit lower, drops by the same amount, so it goes down something like this as time goes on. And finally, my product starts off at 0 and finishes at 0.3, so it would go something like this. So this side here represents the concentrations of my species, and here is time. And a quick look would indicate perhaps at this point we've reached equilibrium because the amounts aren't changing anymore. Let's take a look at another problem. Again, I begin with identifying the initial, the change, and the equilibrium amounts. This time I have a half a decimeter cube container, and I have my amounts. So 0.25 of both of these species. So 0.25 divided by 0.5 will give me starting amounts of 0.50 and 0.50. At equilibrium, I'm found I have 0.1 moles of NO2. So I'm going to take that 0.1 and divide it by a half, giving me 0.20. So I can identify from this that this species is going down. That would then suggest that the product must be going up. So the reaction must be going this way if this amount's dropping. Now I can identify what the change is here. It changed by 0.3. Now what will the change be here? Here the ratio is 2 to 1. So this must reflect that coefficient as well. So the change here would be only half as much, 0.15, to maintain that ratio. So at equilibrium then, I have 0.65 of NO. So let's take a look at what this would look like. Both of them starting off at the same point, and this one goes down to 0.2. So I'll sketch that, say, as something like this. And the other species, starting at the same point, goes up by half as much, so it maybe goes up something like this. And again, sort of from this point on, we've reached equilibrium. This question also asks us to determine what the equilibrium constant is. So our equilibrium constant is our product, N2O4 to the exponent 1, divided by NO2 squared. So putting in our particular values, we've got our product and our reactant at equilibrium. I have to square that value, and that comes out to approximately 16, suggesting favoring the product over the reactant. Okay, in the last problem, I'm going to look at a little bit messier one where the ratios aren't quite as nice. Again, I have a 2-liter container, so I'm going to have to make sure that I convert everything into moles per liter. So 1 divided by 2 makes my starting amount 0.50. 1 mole of H2 in a 2-liter container. And it starts with only these two, so I can make an assumption here that there was none of this present. At equilibrium, 0.6 in the 2-liter container of hydrogen. So this now has reached 0.30. So I can see that this species has gone down, suggesting the reaction went forward, making ammonia and using up that. The change here would be 0.2. Now this ratio, I have to have a 1 to 3 ratio between these two species, so I'm going to divide this by 3, and it's approximately 0.07. And the ratio between this one and this one is 1 to 2, so the change here would be about 0.13. So this goes up to 0.13. This one goes down to 0.43. A quick sketch of what this would look like, again starting at 0.5 for my nitrogen. It's just going down slightly. The hydrogen starts off at the same plateau but drops down a little bit more. And finally then the production of ammonia, my product, starts here and perhaps climbs to here. So again, the difficulty in this one is maintaining that ratio, this case 1 to 3 to 2, which makes it a little bit more complicated. Anyway, we'll take another look at this use of this ICE table in some more complicated programs, more complicated problems in our next program. Thanks for watching.